Hello and welcome to this video for the 2022 Level 3 Complex Numbers exam. So the marking schedule has not yet been released for this exam, so based on any gradings I give for these questions, it's just based on a rough estimate and may not be truly reflective of the actual gradings for these questions when the mark schedule is eventually written by NZQA. However, I'll do my best to give a rough guide for each of the questions and what mark I think they should be worth based on past exam papers and patterns of NZQA marking schedules. So let's just get straight into it. So we have question number 8, write 12k over 1 plus square root of 5k in the form ak plus bk root 5, a and b are integers. Alright, for this question, we want to rationalize the denominator, so we're going to multiply by the conjugate. So I'm going to say 12k over 1 plus root 5. We're going to multiply by the conjugate, which is 1 minus root 5 over 1 minus root 5. And that is equal to 12k times 1 is still 12k. 12k times negative root 5 is minus 12 root 5k. Divided by 1 plus root 5 times 1 minus root 5 is 1 times 1. Minus of root 5 times root 5, which is 1 minus 5. That equals to 12k minus 12 root 5k over negative 4. Sorry, that's not very good. That equals to negative 3k plus 3k root 5. So in this case, a equals to negative 3 and b equals to 3. Let's look at question number B. So in terms of the grading for this question, this is just an achieved question there. If u equals to m5 cis pi over 3 and v equals to m squared cis pi over 5, write u over v in polar form. So in this case, we're going to write u over v first. So u over v equals to m to the power 5 cis of pi over 3 divided by m squared cis of pi over 5. And for this question, the rule is that for the the coefficient will be divided and the angles are subtracted when we do division. So in this case, m5 divided by m squared is m to the power 3. And this will be cis of pi over 3 minus pi over 5. This equals to m to the power 3 cis of 2 pi over 15. And that is our final answer for this question, cis 2 pi over 15. And that is another achieved grade there. For question C, we see if u equals to 3 plus 2i, v equals to 4 plus 2i, and w equals to 2 plus ki, find the value of k if the argument of u times v times w is pi over 4. For this question, I reckon that we should first just multiply u, v, and w to get an expression for the real and complex parts of u, v, w. So now let's start off by multiplying u and v. So uv equals to 3 plus 2i multiplied by 4 plus 2i, and that is equal to 12 plus 6i plus 8i minus 4, and that is equal to 8 plus 14i. And now let's multiply by w, so we have 8 plus 14i multiplied by 4 plus 2i, that is equal to 32 plus 16i plus 14 times 4 is 56 minus 28. Yeah, okay. So this equals to where did I get 4 plus 2? My apologies. I thought something was a bit off. I was like, there's no k's in this expression. Sorry about that, guys. I was gonna say, okay, sorry, so we have 8 plus 14i, and we multiply by 2 plus ki. That's more like it. Okay, so we have 8 times 2 is 16, 8 times ki is plus 8ki, plus 28i. Ki times 14i is I squared is negative 1, so we have negative 14k. So in this case, let's group the real parts together and the complex parts together. So we have this equals to 16 minus 14k, adding this with 8k plus 28i. Okay, so now this will be the expression for u, v, w. And in this case, we want to find the value of k given that the argument is pi over 4. So whenever you're given an argument, I highly recommend that you're drawing out a rough sketch of the argand diagram to see approximately where in the plane that the complex point lies. So in this case, the angle is pi over 4, so we have like pi over 4 here, and our point will be lying across that line. Okay, so in this case, we say that if we have this is equal to y and this is x, we can say that tan of pi over 4 equals to y over x. So therefore, we say that x equals to y. So when I say x equals to y, this just purely means that the real part is equal to the imaginary part. So we can equate these two expressions and then find our value for k. So we can say that 16 minus 14k equals to 8k plus 28. So let's just move everything to one side. So we have 22k equals to 16 minus 28 is negative 12. So therefore k equals to negative 22 over 12. Oh, sorry, other way around. Negative 12 over 22. Negative 12 over 22. Yeah, that's right. And this will be a merit level question. And an achieved level should be multiplying UVW to get an expression for UVW in terms of K. So if you can get up to here, that should be an achieved. Great. Let's look at number D. So find the values of P for which the equation x minus 2 root x plus P equals to negative 5 has one real solution. Alright, so let's get started on the next page. Oh, sorry. Let me just get rid of this. Sorry about that. I thought I cleared it, but apparently I didn't. Okay, apologies. So what we had was x minus 2 square root of x plus p equals negative 5. So in this case, let's move the square roots to one side by itself and then move everything else to the other side. So we have x plus 5 equals to 2 root x plus p. And let's find the square of both sides. So we have x squared plus 10x plus 25 equals to 4 times of x plus p. So x squared plus 10x plus 25 equals to 4x plus 4p. And in this case, we'll have x squared plus 6x plus 25 minus 4p equals to 0. And in order to have, for the polynomial of degree 2 to have one solution, this just means that b squared minus 4ac equals to 0. So recall from level 2, for one solution, b squared minus 4ac equals to 0. So in this case, we'll have 36 minus 4 times of 1 times of 25 minus 4p equals to 0. 36 minus 4 times 25 is 100. 4 times negative 4p is negative 16p. That equals to 0. So negative 64 plus 16p equals to 0. And therefore 16p equals to 64 and p equals to 4. So p equals to 4 is our final answer for this question. And you'll find that the solution is x equals negative 3, I believe it was. So if you solve backwards to find what x is, if p is 4, then you should get a solution x is negative 3, if I'm not mistaken. And this will be a merit level question with a merit for finding the correct p-value. If you want to get an achieved level grade, if you can get up to this quadratic part, so x squared plus 6x plus 25 minus 4p equals to 0, that should be sufficient basis for the achieved grade there. All right, so let's have a look at E now. So apologies. Let me just get rid of everything here. And let's just start off this question. So for complex numbers, w and z, prove that w plus z, modulus squared minus w minus the conjugate of z, modulus squared, equals to 4 times the real part of w times the real part of z. So in this case, it's really easy to just let w be some complex number and then let z be something else, and then prove for the general case that the statement is true. So we say that let w be a plus bi, just arbitrarily, and we'll say that z equals to x plus iy. Alright, so what's w plus z? W plus z is just equal to a plus x plus b plus y times of I. That is w plus z. And w minus the conjugate of z, that's equal to w, which is a plus bi, minus the conjugate of z, which is z minus yi. X minus yi, and that's equal to a minus x plus b minus is plus, so that's b plus yi. Beautiful. So let's get an expression for the modulus squared. So in this case, the modulus is square root of, for example, w plus z would be a plus x squared plus b plus y squared, and this whole thing squared minus of a minus x squared plus b plus y squared, square root, the whole thing squared, and then the squared and the square root cancel each other out. So we will have a plus x squared plus b plus y squared minus a minus x squared minus b plus y squared. And this will cancel each other out. And let's expand and simplify. So we have a squared plus 2ax plus x squared minus a squared plus x squared minus 2ax. So this will give us a squared plus 2ax plus x squared minus a squared minus x squared plus 2ax. So that cancels with a squared and x squared, and we will have 4ax. But what is a? A is equal to the real part of w. What is x? X is equal to the real part of z. So this just simplifies down to 4 times the real part of w times the real part of z, which was required. So as required. And this should be an excellence level question here for, sorry, I probably should use T. So this is an excellence level question for getting the correct proof. For a merit grade, if you can get up to simplifying up to somewhere here, I'll say maybe somewhere here it could be a merit. And for finding an achieved grade, if you can just get up to just basic understandings here, it could be an achieved. Brilliant. Let's look at question number 2. Dividing x cubed minus 3x squared plus bx plus 9 by x plus 2 gives a remainder of 3. Find the value of b. So in this case, we're just going to be using the remainder theorem. So if we plug in this case, x equals to negative 2, we're going to get a remainder of 3. So if we say that this is f of x, we know that f of negative 2 equals to 3. And we can use that to find b. So negative 2 cubed is negative 8 minus 3 times negative 2 squared minus 2b plus 9 equals to 3. And should get that. We have negative 8 minus 12 minus 2b plus 9 equals to 3. And we should see that 2, what am I doing? Okay, so 3 minus 9. So 2b equals to 14, and therefore b equals to 7. And this should just be an achieved question there. 2b equals, let me just double check that one. So we have 3 minus 9 plus 12. Oh, sorry, negative 2b. My apologies. Yeah, I thought something was not quite right there. So negative 2b equals to 14. So b is negative 7. Apologies there. And yeah, that's the achieved level question. Let's have a look at question B. Find the complex number z for which z plus 4 modulus, conjugate of z equals to 15 plus 12i. So in this case, we can say that z is equal to x plus iy, and the conjugate of z is therefore x minus iy. So in this case, we have x plus iy plus 4 times of x minus yi equals to 15 plus 12i. And in this case, we have x plus 4x plus yi minus 4yi equals to 15 plus 12i. And we have 5x plus minus 3yi equals to 15 plus 12i. And in this case, we just have this very simple case of the real part is equal to the real part and the imaginary part equal to the imaginary part. So in this case, we'll just have 5x equals to 15, x equals to 3, and we will have negative 3y equals to 12i, and therefore y equals negative 4. So x equals to 3 and y equals to negative 4, and we should find another achieved grade here. Question C. One of the solutions of z to the power 3 minus 2z squared plus hz plus 180 equals to 0 is z equals to negative 4. Find the other solutions in the form a plus bi and the value of h. So for this question, we know that z equals to -4 is a solution. And by the definition of a solution, we know that since -4 is a solution, if we plug -4 back into our polynomial, we should get the result of 0. Because z equals to -4 makes the equation true, so the left-hand side equals to 0. So in this case, we can just say that -4 to the power 3 minus 2 times 4 squared minus 4h plus 180 equals to 0. So -64 minus 32 minus 4h plus 180 is equal to 0. So -4h equals to -84, and therefore we get h equals to 21, which is a brilliant start. So now we know about the polynomial we want to find is z cubed minus 2z squared plus 21z plus 180. To find the other two solutions, we want to use a polynomial division in order to find a quadratic, and then we'll use the quadratic formula in order to find the two solutions in the form a plus bi. So how do we get the divisor for the polynomial? In this case, we know that z equals to -4 is a solution, so therefore z plus 4 divides the polynomial. Okay, divides polynomial. So in this case, we have z to the power 3 minus 2z squared plus 21z plus 180 divided by z plus 4. So let's just chug, to get rid of the x to the power 3, we chug in x, z, why do I keep saying x? Okay, we chug in z squared, so we should get z to the power 3 plus 4z squared, and -2 minus 4 is -6z squared plus 21z. To get rid of the -6z squared, we're going to use -6z. So we're going to get -6z squared minus 24z. So in this case, we'll have 21 minus of minus 24, which is positive 45z plus 180. And we're going to add 45 along at the end. Yeah, and that will give us, that will be 45z plus 180, and that's 0, as expected. So that's brilliant. So now we have our quadratic, which is, let me just work over here. We have z squared minus 6z plus 45. So z equals to 6 plus or minus square root of 36 minus 1 times of 4 times of 45 all over 2. So z equals to 3 plus or minus 1/2 square root of, okay, let's just evaluate this one. 36 minus 4 times 45, that is -144. So now we have z equals to 3 plus or minus square root of 144 is 12. So we have 6i here. So we have z equals to 3 plus or minus 6i will be our solutions. So we have solutions would be z equals to 3 plus 6i, 3 minus 6i, and -4. And that's our completion for this question. Quite a lot of work, to be fair, but it is what it is. And to get a merit grade for this question, you should be able to find all three solutions and the h value. So both would be a achieved grade. And if you can find the value of h, I'm pretty sure that should be an achieved. So there. Brilliant. So let's look at question number D. If z equals to 1 minus root 3i and w equals to 4 over z minus 2, find the argument of w. Alright, so let's work on getting an expression for, expression for 4 over z minus 2 first. So we have w equals to 4 divided by 1 minus I root 3 and minus 2. So to evaluate 4 over 1 minus I root 3, we need to multiply by the conjugate. So we get w equals to 4 over 1 minus I. So we've got multiplied by 1 plus I root 3. 1 plus I root 3 and 1 plus I root 3. And that is equal to 4 plus 4i root 3, all divided by, what am I doing? 1 times 1 is 1, and we have 1 here. I root 3 times negative I root 3 times I root 3 is negative I squared 3. I squared is 1, negative 1. So negative 1 times negative 1 is positive 3. So that's a positive 3 there. So this equals to 1 plus I root 3. Perfect. And we know that W equals to 1 plus I root 3 minus 2, which is negative 1 plus I root 3. To find the argument, we're going to be drawing drawing a rough sketch of where W lies in the Argand plane. So in this case, we have a negative, which is on the left here, negative 1, and we have a root 3, which is here. So in this case, this length of the vertical is root 3, and the length of the horizontal is 1. So we have this angle theta. So we have tan theta is equal to root 3 over 1. So it's just root 3. So tan inverse of root 3. That will give us theta equals to pi over 3. If theta is pi over 3, remember that the argument goes from the right-hand x-plane here. So if that theta is pi over 3, then the argument would be here. The argument would be the whole of the argument would be pi minus pi over 3, since pi is equal to the angle of the straight line. So we have argument is equal to pi minus pi over 3, and that is equal to 2 pi over 3. And that should be another merit level question there, where you should be able to get an achieved grade for finding the W. So if you can find W, that should be an achieved. Find the Cartesian equation of the locus described by the modulus of z plus I equals to 2 times the modulus of z minus 5i. So in this case, we're going to let z be equal to x plus iy. Z plus I is equal to x plus y plus 1 of I. So we have x plus y plus 1 of I. That is equal to 2 times of, we have x plus of y minus 5 of I. And let's write this in the modulus form. So we have x squared plus of y plus 1 squared equals to 2 times root of x squared plus y minus 5 squared. So in this case, we have x squared plus y minus 1 squared. So this is just squaring both sides. Plus 1, sorry. And that's equal to 4 times of x squared plus y squared minus 10y plus 25. So we have x squared plus y squared plus 2y plus 1 equals to 4x squared plus 4y squared minus 40y plus 100. So let's move everything to the left-hand side. So we have 0 equals to something on the right. So we have 0 equals to 3x squared plus 3y squared. Negative 40y minus 2y is negative 42y. 100 minus 1 is 99. And the good thing is that we can see that every number here is divisible by 3. So let's divide both sides by 3. So 0 equals to x squared plus y squared minus 14y plus 33. Alright, and we need to write this in the form of x minus a squared plus y minus b squared equals to k squared. So let's write y squared minus 4y as y minus 7 whole squared. So you have 0 equals to x squared plus y minus 7 whole squared plus 33. And in this case, since we have negative y minus 7 squared, that's if we expand y minus 7 squared, we're going to get y squared minus 14y plus 49. So the plus 49 wasn't there before. So if we add 49 to the right, we also have to add 49 to the left in order to make it equal to each other. So don't forget to add the 49 here on the left. Alright, so let's subtract 33 from both sides. So we have 49 minus 33 is 16, and that is equal to x squared plus y minus 7 squared. And that is in the form required. So in this case, we have a circle. So this is a circle with center. The center is 0, 7, and the radius is 4. If we want to describe the locus, that would be our answer. So the circle is radius 4 with a center of 0, 7, and that would be an excellence grade there. To get a merit grade, if you can get up to, I reckon, around this step, but you're not in the correct form, so if you just have it in this x squared plus y squared minus 14y plus 33 form, that should be grounds for a merit grade. In terms of getting an achieved grade, I think we're looking at possibly just being able to rewrite in the modulus form correctly. So maybe somewhere here that might be an achieved grade there. All right. Question number 3. The complex numbers r and s are represented on the Argand diagram below. If v equals to 2r minus s, find v and mark it on the Argand diagram above. Alright, so let's just get the values of r and s first. So we're just reading off the real and imaginary parts from the graph. It's pretty simple. So we have r equals to 3 plus 2i. S equals to 2 minus 5i. And v equals to 2r minus s. So v equals to 2 times of 3 plus 2i minus of 2 minus 5. So v equals to 6 plus 4i minus 2 plus 5i. That is 4 plus 9i. That is v, and let's mark it on the Argand diagram. So the real part is 4, and the real part is 4, and the imaginary part is 9. So we have this should be right here. Sorry, it's not very neat. Let's try again. Yeah, and that should be our v value there. 4 plus 9i. So this should just be a very simple achieved question here for the correct answer and correct marking on the Argand diagram. So 4 plus 9i. Great. Solve the equation z squared plus 6kz plus 15k squared equals 0 in terms of k. Give your solution in the form ak plus or minus square root of bki. So in this case, we're just going to use the quadratic formula. Pretty straightforward here. So we have z equals to negative 6k plus or minus 36k squared minus 4 times of 1 times of 15k squared all over 2. So z equals to negative 3k plus or minus 1/2 of 36k squared minus 60k squared, which is negative 24k squared. So z equals to negative 3k plus or minus 1/2 of I square root of 24k squared. And 24, square root of 24 can be rewritten as square root of 4 times square root of 6. Square root of 4 is 2, so that cancels out with the 1/2. So in this case, we'll have z equals to negative 3k. Plus or minus, in this case, our 1/2 cancels out, so we have ik root 6. Ik root 6 should be our answer for this question. So negative 3k plus or minus ik root 6. So a equals to negative 3 and b equals to root 6. Oh, 6, just 6. B equals to 6. And that should be another achieved grade here. Alright, let's have a look at question number C. Solve the equation z cubed plus k to the power of 6i equals to 0. K is a real constant. Give your solution in polar form. In this case, we're going to make z cubed the subject. So we have z cubed equals to negative k to the power of 6 times of I. We want to rewrite negative k to the power of 6 times of I in a cis form so we can easily find the 3 roots of the equation. So to do this, we're going to map it out in the Argand diagram. So we have negative k to the power of 6. We know that k is a real constant, and any constant to the power of an even power will be positive. So k to the power of 6 is positive, or equal to 0, positive or 0. And we know that negative k to the power of 6 is negative, okay? So therefore, our location of negative k to the power of 6i would be somewhere here. We'll just say this is negative k6. And this is the imaginary part, the real, okay. So to write this in cis form, we can take note of the argument. So the argument here is negative pi over 2. And we know that the modulus here, the length is k to the power of 6. So we know that z to the power of 3 is k to the power of 6 cis of negative pi over 2. Alright, so let's take the third root on both sides. So we have z1 equals to k squared cis of negative pi over 2 divided by the power, which is 3. So we have negative pi over 6. So that's our first solution. Our second solution is z2 equals to k squared cis of negative pi over 6 plus 2 pi over 3. The reason it's 2 pi over 3 is because we have 3 solutions for this equation. Because it's a third degree polynomial, we're going to have 3 solutions. A full circle is 2 pi radians, so each of the solutions will be located an angle of 2 pi over 3 away from each other, so a third of the circle away from each other. If it was z to the power of 5, then it would be each solution would be spaced 2 pi over 5 away from each other, so you'll be adding 2 pi over 5 each time. But since it's z to the power of 3, each solution we're just going to be adding 2 pi over 3 to the angle to find our next solution. So that's just k squared cis of, in this case we should get pi over 2. And let's do it again. So we have z to the power of 3 equals to k squared cis of pi over 2 plus 2 pi over 3. And that is equal to k squared cis of negative 5 pi over 6. And that's also the same as k squared cis of 7 pi over 6. However, we prefer to write it as the absolute value of the angle is less than pi. So in this case, we just rewrite it, but looking from the anti-clockwise direction, negative 5 pi over 6 equals to 7 pi over 6. So those are the 3 solutions of the equation. Those are the 3 solutions, and that should be a merit level question here. So merit level question to find all 3 solutions, and achieved is usually if you can just find like one solution, maybe like if you can get up to z, the first solution is k squared cis of negative pi over 6. That should be enough for a achieved grade. All right, question D. Prove that there is no complex number z such that the modulus of z minus z equals to I. So let's assume there is such z. So we're going to say z is x plus iy. So that the modulus of z is equal to x squared plus y squared square root of x squared plus y squared. So therefore, modulus of z minus z is equal to square root of x squared plus y squared minus x plus iy, and that is equal to x squared plus y squared minus x minus yi, and that is equal to I. So again, in this question, we have a very simple idea that is used a lot in the complex exam. It's just that the real part of the equation is equal to the real part, and the imaginary part is equal to the imaginary part. So in this case, the imaginary part is just negative yi. So therefore, negative y equals to 1. So y equals to negative 1. So let's chuck in y equals to negative 1 into our real equation. And we want to say that the real part is equal to 0. The reason that the real part is equal to 0 is because it's just I and it's equal to I plus 0. So we have x squared plus 1 minus x equals to 0. Let's move x to the other side. So we have x squared plus 1 equals to x. So x squared plus 1 equals to x squared. And therefore, if we cancel out the x squared, we'll say that 1 equals to 0. So this equation is never true. So never true for any x in the real. So this is not true for any x in the real plane. So therefore, there is no solutions for z such that modulus of z minus z equals to I. So since never true, no solutions. And that will be another merit level question here. With an achieved grade, if you can identify that y equals to negative 1, I think that could be enough for an achieved. Or you can just give like a vaguer argument or something you might drop down to an achieved. So like vagueness in your answer maybe. That might drop you down to an achieved if you do that. Okay. Let's look at the final question, question E. If z equals to a plus bi, and it's a non-zero complex number, and I over z plus 3 over conjugate of z equals to 1, find the values of a and b. All right, so z equals to a plus bi. So let's write out this expression. So we have I over a plus bi plus 3 over a minus bi. Usually, if we wanted to multiply by the conjugates, we would do each one of these individually. So multiply by a minus bi plus a plus bi for the a minus bi. But notice that for these two fractions, that the denominators are the conjugates of each other. So a really easy hack is just adding these two fractions as if you're adding any two fractions. So if you just immediately just multiply like this, so plus 3a plus bi over a plus bi, a minus bi. Notice that on the denominator, we already have the conjugate multiplied by z. So therefore, the good news is that it's already going to be a it's already going to be a real denominator after we compute this fraction. So we have ai plus bi times I is bi squared, which is negative b, plus 3a plus 3bi. And that is over a squared plus b squared. And that is equal to 1. So multiplying both sides by a squared plus b squared is a squared plus b squared equals to ai minus b plus 3a plus 3bi. So in this case, again, with question D, we're going to be making the real part equal to the real part and the imaginary part equal to the imaginary part. So the real part is on the left-hand side is a squared plus b squared. That's equal to 3a minus b. The imaginary part on the left-hand side is 0. So 0 is equal to the imaginary part on the right, which is 3b plus a. If we rearrange the second equation, so we have equation 1 and equation 2. If we rearrange equation 2, we're going to get a equals to negative 3b. And let's plug a equals to negative 3b back into equation 1. So we have negative 3b squared plus b squared equals to 3a is 3 times of negative 3b minus b. Alright, so in this case we have negative 3b squared is 9b squared plus b squared. That is equal to, what is that? 3a minus b. Did I make a mistake somewhere? Sorry, I think I may have made a mistake somewhere. So we have a squared plus b squared equals to ai minus b plus 3a plus 3b. Looking 3a plus 3bi. Yes, sorry. This is sorry guys. That's a minus and that's a plus here. Yeah. Sorry about that. That's a bad mistake. So just change this to plus. That's a plus. That's a plus. Okay. So 9b squared plus b squared equals to 9b plus b. So 10b squared, 10b squared is equal to negative 8b. And therefore we have, maybe we can here, so 10b squared plus 8b equals to 0. b times of 10b plus 8 equals to 0. Therefore, b equals to 0, or b equals to negative 4 over 5. And since we know that the solution is non-zero, so non-zero complex number, so b equals 0 is not a solution. So b equals to negative 4 over 5, and a equals to negative 3 times b. So a equals to 12 over 5. So that's our answer. So a equals to 12 over 5. And b equals to negative 4 over 5. That should be our final answer for this question. And that should be an excellence level grade if you can get up to here. You can get a merit level grade if you, if you are able to find these two equations maybe. That would be sufficient evidence for a merit. And achieve could possibly just be like minor progress. So I would count this as like decent amount of progress if you're talking about an achieved grade. I reckon that's decently okay progress that could be an achieved. And alright, I think that's all the questions for this test. Yeah, that's all for this exam. And if you have any questions, please leave it down in the comments below. And I hope to see you all in the next one.